And we start with Dr. Ron Cohen from the Geophysical Lab, who will be talking about the fundamental theory that we all come to use, which is density functional theory. We ask some of you that you should know some of this, but for us, this school is actually going beyond this existing theory that was developed in the 60s. It's basically the question, what are we going to do in this century? Are we still going to use density functional theory, or is there something more fundamental, more exact, that maybe 100 times more, require 100 times more computer time, but will actually get you the answers that you need to compare with these experiments. So thank you very much for coming, and hope you have a good week.
Okay, so I'm going to start out not talking about quantum Monte Carlo itself, but this is really in some ways a prerequisite. Is this on? Test. No.
You have to press it on for a little while.
Okay.
And you put it maybe on your time, and not so far on the side, put it in the center.
Okay. So I'm going to talk about really a prerequisite for doing QMC with modern codes. And many of you may already have a background in DFT, and for you, maybe much of what I'll be saying will be review. I find that this kind of review is useful anyway, and I'll be showing some examples that maybe you're not so familiar with. And I'll try to motivate a little bit why we need QMC as well, with some examples where DFT methods don't work so well. So Burkhard specifically asked me to not say in my second slide I don't have time to talk about this, so hopefully I won't do that. So I see I started out with an old heading on this slide, but I'll move on to a new talk. Okay, so this is an outline of what I'm going to talk about. I'm going to give some motivation about why we need QMC, and also talk about what DFT is used for in QMC studies, because in most, I would say, or many DFT studies, QMC studies, one starts with density functional theory. This doesn't really belong here. So density functional theory, I'll go through really starting from the beginning, starting with the Hohenberg-Cohen theorems, and work all the way up to pseudopotentials. And really, what I'm going to talk about is really the basis for a whole short course on DFT, except squeezed into a little over an hour, or an hour and a half. So it may go by a little bit quickly. You will have access to the slides, of course, so you can see all the equations at your leisure and take time to look at the references and learn about it if you don't know about this. Many of the slides that I'm going to show are really the basis of whole lectures, say in a DFT short course. So you'll just have to, without taking the whole week to talk about DFT, there's really not any alternative way to deal with this. So let's start out with just what's density functional theory, because maybe some of you are not familiar with it at all. And even people that are familiar with it maybe have some basic misunderstandings about it. Sometimes people call DFT a single particle theory. It's not. It's an exact many-body theory. Okay, so DFT is an exact many-body theory for the ground state properties of any electronic system. And it deals with anything, atoms, molecules, surfaces, nanosystems, whatever. Although it's formally exact, and I'll even show you an equation for the exact way to do DFT, the exact functional that's usable is not really known. Okay, so we have approximations, and I'll talk about some of those approximations and about how well they work. Even if there is a usable exact functional, it's probably a mess. So nobody has found it yet. Maybe someone will. But in any event, it's going to be something extremely non-local and probably as difficult to do or worse than doing QMC. So QMC in some ways can be thought of as a way to do exact DFT. I'm not going to push that point of view, but you could think of it that way. We do have some very good approximations, but they work well for kind of subclasses. They work for certain types of materials very, very well, and then as soon as you get outside of that sphere where they work well, things start to break down, and I'll show some examples of that. In practice, DFT is quite good for structural stability, vibrational properties, elasticity, equations of state, but when I say quite good, it's never going to give you any kind of exact result in real applications. It's always going to be approximate. It's not the kind of thing that you just run for longer or increase your basis set size and eventually you reach the exact answer. So even when you completely converge a DFT calculation, there's going to be some error compared with reality. Okay. Let's see, what do I have to do? Okay. So let's start with what density functional theory is. So I said it's an exact theory dealing with the ground state properties of an electronic system. Oops. Okay. And in practice, what one has to do is solve a set of what are known as, and I'll show where this comes from, the Cohen-Sham equations, which look like single particle Schroeder equations. So that's why many people think of it as a single particle theory. So they're just a set of separate single particle three-dimensional differential equations, but they have an effective potential which encompasses the many-body nature of the system. And in fact, I'll be showing you that there's a proof that such a solution actually exists, such a form exists. Okay. So the potential here is a sum of really two parts. The first part is the electrostatic potential, which of course we know exactly, the electrostatic interactions between electrons and nuclei, and between electrons and other electrons. And then the so-called exchange correlation potential, which encompasses all of the many-body aspects of the problem. And we can think of the total energy system of the system as being a sum of different terms. We have kinetic energy, which is basically the kinetic energy of the non-interacting particles, like the non-interacting electrons. The electrostatic energy between the electrons and between the electrons and nuclei, and then this exchange correlation energy. And there's a little trick here, which is very nice to do when you can do it, and when you can get away with it, is we say it's an exact theory, and we do that by saying, by definition, this exchange correlation energy is the energy that you put in that makes the theory exact. Okay, so by definition, it's an exact theory. Okay, so all approximations come in what this exchange correlation energy is. Now we happen to know the exchange correlation energy quite well for a uniform electron gas, and we know that from Dave Sepperly's work with quantum Monte Carlo. Okay, so quantum Monte Carlo is really built into the fundamental basis of density functional theory. A lot of people don't think of that. But the fact that we know the exchange correlation energy for a uniform electron gas, it could have just meant that we could do a really good job studying the uniform electron gas. But it turns out, just by good luck, that if you apply that to any system, even a very non-uniform system like an atom or a crystal or a molecule, it's still quite a good approximation to treat it locally as if it was a uniform electron gas at each point of that density. I'll be talking more about that as well. Okay, so first just a few examples to show how well DFT works and the fact that you really can do real stuff with it. Oops. So consider something like magnesium oxide, which is a very simple ionic material, but it's a little bit non-simple in that the oxygen is quite big and very polarizable. And so you really can't think of MgO as being just classical spheres of charge. But we can calculate quite sophisticated properties of MgO, for example, with DFT and get very good agreement with experiment, even predicting properties that had not yet been measured. This is work for many years ago now, but for example, if we look at something like equations of state, thermal equation of state like the thermal expansivity, we get really within experimental error, not only at zero pressure, but also at very high pressure. If you look at the thermal expansivity here measured in shock experiments up to almost 2 megabars, these show the error bars from the experiments. You see the calculations done some years before the experiments originally really agree quite well, will really go right through the error bars. If we look at something like phonon frequencies, the experimental phonon frequencies are shown here in dots for magnesium oxide, and you see the curves here go right through the points. So really you can get extremely good accuracy and prediction. If we look at something like diffusion, then this was again an area where it wasn't clear that the experiments were even going to be possible to look at diffusion under high pressure in magnesium oxide, but the predictions were really in perfect agreement with later experiments that were done. So you see it's a predictive model. It doesn't just allow us to understand or explain experimental results, but even make quantitative predictions. This is another DFT example, a more complicated material, stishovite in the SiO2 structure. And, oops, I don't know why this keeps happening. Anyway, it was believed to have possibly a very high pressure phase transition, but nobody knew where it was going to be. And we did calculations that showed that that there was a transition at about 50 GPa, and that it should be detectable by seeing this Raman mode go down in frequency and then go up as you went past the phase transition. This is an important material as it's the simplest high pressure silicate that can form in silica-rich areas in the Earth. And this shows also experimental data that had been done at lower pressures, but they hadn't gone up to such high pressure yet. And so the basis of a PhD thesis by Kathleen Kingma was to do the Raman experiments at higher pressure, and found a really perfect agreement with the predictions. So again, we have a predictive theory that can predict properties of materials. I don't want to belabor this too much, but just another example is looking at another simple material. This should say Al2O3 up here, aluminum oxide. And using, again, just straight DFT, there were a series of different approximations and done over the years, and predicting high-pressure phase transitions, which were then observed in experiment. Not only were they observed to be qualitatively correct, but within really 1 or 2 GPa of the predicted transition pressures. So to tell you the truth, it's hard to even make such accurate predictions with QMC just because of numerical issues, not because of anything fundamental. But with DFT, one can do the numerics essentially perfectly, and it's accurate enough to predict these kind of phase transitions. Another example, just running through this set of examples with some geophysical flavor to them, is getting some idea of the temperature at the center of the Earth. And by the way, there's whole websites devoted to putting a religious spin on this. Okay, so apparently Lars Stixrud and I found the temperature of hell by finding the temperature at the center of the Earth. So this has become very popular in some corners of the internet. So what we wanted to do was see how hot it was in the center of the Earth by looking at the elastic properties of iron as a function of temperature. And this is the bulk modulus and the shear modulus that we predicted as a function of temperature. And these horizontal lines are the seismological measurements of the shear and bulk moduli of the inner core of the Earth that are obtained by looking at free oscillations of the Earth. So the Earth kind of rings like a bell, and seismologists study this ringing and can determine the sound velocities as a function of depth in the Earth. They can also do this from seismology. Now, seismology is not so sensitive to the shear modulus in the inner core of the Earth, because the inner core of the Earth is surrounded by a liquid outer core which does not support shear waves. But using a combination of seismology and free oscillation studies, there's some quite accurate estimates of the elastic moduli of Earth's inner core, which is believed to consist of iron. So we calculated the shear and bulk sound velocities and moduli of iron as a function of temperature, and ended up with a temperature of about 6,000 Kelvin, which is probably the best estimate we have of what that important temperature boundary condition is. So conventional band theory and density functional theory has really been used for thousands and thousands of studies now. If you look at any copy of Physical Review, I don't know, maybe half of the papers in there these days our DFT papers. So it's generally speaking, tremendous amount of success. And there's cases that don't work so well as well. An example is here. I already talked about how we predicted phase transitions in Stishovite, in SiO2, using density functional theory, and where it worked very well. But where it starts to fail sometimes is when comparing the energies of different structures. And this is a famous paper by Don Hammond from, what is the year there?
96.
Yeah, the 90s, 96, showing that if you apply the local density approximation, which I'll be explaining in a few minutes, to quartz and Stishovite, so it's a low density version of SiO2 and a high density version of SiO2, then the local density approximation makes the high pressure form be actually the zero pressure form. So it incorrectly predicts this relative energy difference. Whereas if you apply this generalized gradient approximation, which I'll be talking about briefly, it gives the right energy difference between the phases and correctly predicts quartz to be the ground state phase. So this kind of result, at the time that it came out, that Hammond published this, the idea was that if you use an accurate enough density functional, you'll get the right answer. And certainly certain approximations, like the local density approximation, again, which I'll be explaining in a minute, doesn't work so well. But if you use a better approximation, it does. But this is actually work of Kevin Driver, who's one of our lab instructors at this school. So looking at the transition pressure, you see that if you apply the more accurate functionals, you get better agreement with experiment, whereas the LDA even gives the wrong sign for the transition pressure. But if you look at some other property, like the bulk modulus, you see the opposite picture, where the LDA gives a very good agreement on the compressibility of quartz compared with experiment, and the GGA does a much worse job. So actually the picture is not so rosy as many people thought, and it looks like maybe you choose a different density functional for a different property, and that would be a very bad way to do physics. Nevertheless, it's a decent approximation, but still you see that you have very appreciable errors in the bulk modulus from the so-called better functionals. If you apply even more accurate density functionals, it doesn't get any better. Okay, so basically this fundamental problem remains. It doesn't seem like, well, you just need to go one step better and then eventually you'll get the right answers. There's always this trade-off between one property and another. You can look at the difference, as I'll be explaining in a minute. Density functional theory's fundamental quantity is the charge density. And so you would think, well, maybe we'll look at the charge density and we'll understand what's the difference between these different density functionals and be able to fix it somehow. Well, it's not so easy to do. This shows the charge density difference in quartz between the LDA and the GGA, so two different density functionals. And everything green here is where there's essentially no difference in charge density. So they're predicting the same charge density. The whole scale here of this picture is, I think, plus or minus 1/100th of an electron per cubic Bohr. So you're only seeing tiny changes in charge density around the cores of the atoms, where, according to conventional perspective, like I'll talk about when I talk about pseudopotentials, they're not supposed to be involved in bonding and not supposed to be important. That's the only place we're seeing any changes. And so basically different density functionals are giving kind of different sizes of the ions, and nothing sophisticated, nothing interesting like a change in the way the bonding occurs or something like that. So this is kind of a fundamental issue. It also means that when we do QMC, and that you'll be learning about in the rest of the course, accuracy is a big issue. Okay, you can't do a sloppy QMC calculation and expect to get the right answer, because you can see that very small differences can make big differences in your final result. So what do we use DFT for in QMC? So now let's say we've made our decision, we looked at the results for quartz, for SiO2, and we decide, okay, I've got to do QMC because DFT just isn't reliable enough, because I've got to get the right answer. Okay. So first you should start with DFT. Okay, so my view, everybody may not agree with this, that you should still do a set of DFT calculations first and get your hands wet, understand the system, and because you can do them on a laptop in a few hours, and the QMC is going to take you the rest of the year or two. You know, so you might as well understand what you're dealing with first with DFT. So you can explore the system with DFT. You can use it for things like relaxing ground state structures. Generally speaking, we may hear about some advances at this course, but generally speaking, QMC is not used for relaxation of crystal structures. Even when we do QMC, we usually will use DFT to compute phonons, at least in geophysics or anything where temperature is important, we need to estimate thermal properties. We'll use DFT on top of the QMC calculations to deal with that. Even if you're not going to do much with DFT numerically, we can still use it to generate trial wave functions for QMC. You can also use Hartree-Fock or other quantum chemical methods for that. Very often it's convenient to use DFT for that. And sometimes DFT is also used to estimate finite size corrections to QMC. I don't know if anybody's going to be talking about that at the course or not, but you'll find many papers on that subject in the literature. Okay, so that was all by way of introduction. And now we have basically a short course on DFT, compressed into the remaining hour. So maybe I should, I don't know if there's any questions up to this point, but just so people understand where we are now so that we can get kind of started with the nitty-gritty. Are there any questions at this point? I mean, I may not have given anything that really needs a question at this point, but you interrupt me even during the talk if I say something that's not clear. Okay, the fundamental place we start with DFT is with the Hohenberg-Cohen theorem. Which is an exact theorem. I mean, it's a mathematical theorem, and I was going to go through it. I'm actually not going to, so I'm just going to say it's very straightforward, really, but it just takes too much time. So it basically proves that that there's a one-to-one correspondence between the exact many-body wave function, whatever it is. I'm not saying single determinant or anything. Whatever the exact many-body wave function is. The external potential, which is the nuclei in the system we're going to talk about, like what the crystal structure is, and the charge density. And this is really an amazing thing right here, because the charge density is just a three-dimensional object, and the exact many-body wave function is, I guess, an n-dimensional object. Where n is, on the order of 10 to the 23rd particles or something like this. So to go from 3 dimensions to the 10 to the 23rd dimensions is an enormous reduction. So that's the first Hohenberg-Cohen theorem, is that there's this one-to-one correspondence. Now, the thing that the Hohenberg-Cohen theorem doesn't address is whether every potential has a solution in terms of there being a charge density that goes with it, or that every charge density can be represented by some potential. So there may be systems where the Hohenberg-Cohen theorem, it's not that it isn't true, it just doesn't have anything to do with the system, because this is just stating that there are such systems that have this relationship. The second Hohenberg-Cohen theorem is that there's a minimum principle for the total energy as a function of the density. So that in principle, if you just vary this three-dimensional charge density until the energy is its lowest amount, then that lowest quantity, then that would be the ground state, correct ground state density and the correct energy for that system. Notice that this is a functional. So what is a functional if you're not familiar with the word functional? A functional is something that turns a function into a scalar. So a charge density is a three-dimensional function, and the energy is a functional of that density. Okay, so that you plug in the whole three-dimensional density and you get out a number, which is the energy. Kind of a corollary of this is that all of the ground state properties of a system are functionals of the charge density, because they all can be computed from the ground state many-body wave function. And so any property in the world that you're interested in that can be represented as a ground state property should come out right in density functional theory. And you'll find papers, especially in the early days of DFT, where people argued about whether something was a ground state property or not. So for example, the band gap, okay? In fact, maybe you'll still find people arguing about this. So one can make an argument that the band gap of a system is a ground state property, even though it's really the energy of exciting a particle in an insulator across the gap, so you'd think it's an excitation energy, but you can design kind of thought models where you can do a set of ground state calculations to get that energy, and so therefore it should be something that comes out right in the exact density functional. So we can write the Hamiltonian in density functional theory as a sum of terms here, and it looks like I left out the, or just mislabeled one here. But we have the kinetic energy, which is the kinetic energy here of non-interacting particles. And then we have the one-body potential energy, which is the potential energy of, say, the electrons in the nuclei or the cores of the atoms. And then we have the two-body potential, which is the interaction between the electrons. And then in DFT, one has an additional. So this is the Hamiltonian for the exact system, which is replaced in density functional theory by an effective potential, which takes care of the many-body interactions. Okay, well, the Hohenberg-Cohen theorem was very interesting, but it wasn't until Cohen and Sham showed how to use it that it really exploded and blossomed. This was done in the 60s. I guess I don't have the reference written up here, but can easily supply to you if you're interested. So the Cohen-Sham theorem gave our approach gave a set of self-consistent equations for finding the ground state properties. So and this is what we actually do in some form when we do DFT. So I said that the energy is a function of the density, and this is the way we can write that energy then. So there's the so-called Hartree energy, which is the electrostatic energy of the charge density, and the potential from that charge density. There's the kinetic energy, this TS, which is the non-interacting kinetic energy. And then there's the interaction of the charge density with itself. By the way, I'm not going to have time to talk about it today, but I did it for hard, but it wasn't in my second slide. It's interesting to point out, though, that this includes an interaction of the electron with itself. So that needs to come out in this other term here in the exchange correlation energy, which most forms of DFT do not do exactly. So for example, one of the problems with DFT is if you imagine a hydrogen atom with a single electron, it would show some electron-electron interaction, but there's only one electron, so it shouldn't be there. So you can correct for that in a way that's called self-interaction corrections, or you can apply a higher order form of density functional theory to take care of that problem. But most of the calculations that are done in the literature have that problem intrinsic in them, and some of the errors in DFT that you see may be due to that so-called self-interaction. Okay, so Cohen-Sham, remember I said that this exact exchange correlation energy is the energy that you put in that makes the theory exact. Okay, so in principle, it also includes the interacting part of the kinetic energy. So I said that this kinetic energy is the non-interacting part of the kinetic energy. So this must have some kinetic energy piece in it as well. Okay. So now what we're going to do is just this definition first. We're going to define the functional derivative of the energy, exchange correlation energy with respect to density, to be the exchange correlation potential. And so this is the thing that's actually going to be very important in determining properties. I'll show you how this is used in a minute. And so our minimum principle from Hohenberg-Cohen says that if you make any variation in the density, then the ground state energy can't change. Okay, so the derivative of the energy with respect to density has to be 0. And then we have to have some normalization condition. We're going to deal with a system with a charge balance system with a fixed number of electrons. So the number of electrons is going to be the integral of the density over space. So either per volume or per unit cell or in a finite molecule or atom over the whole system. So we want to solve this problem of the minimum of the energy with the energy as a minimum with respect to density by using a Lagrange multiplier mu here on the total number of electrons. And we're going to make some more definitions. We're going to define the Hartree potential to be this integral of the density divided by R. And then what we can show is that we have this equation that needs to be solved, which is the functional derivative of the kinetic energy with respect to density plus the electron nuclear potential plus the Hartree potential plus the exchange correlation potential is equal to this Lagrange multiplier. So if we knew the exchange correlation potential exactly, and if we knew this kinetic energy form exactly, and if they were just simple functions of density, we could solve for the density exactly. And in fact, but we don't. So in fact, we need a good approximation. By the way, I should say maybe right here, which is, again, an area I'm not going to be going over today, but this is really the basic start of a whole branch of DFT known as orbital-free DFT, and you'll find a whole literature on that, where people try to find closed form approximations for solving this equation, and the advantage there is that it's very fast, and they move on from that point of view. Okay, but what we're going to do is follow the set of steps that Cohen-Sham originally solved. So what they said is we do know how to solve for a non-interacting system. So imagine that we have a non-interacting system, so there's no electron-electron interactions. They're just like uncharged electrons, if you will. And what we do to solve it is solve a set of single particle Schrödinger equations. So we just have, this is the kinetic energy piece. This is the interaction between, say, the electrons and the nuclei, but we're going to say there are no electron-electron interactions. And so we have an eigenvalue problem where we have a set of energy eigenvalues and then these eigenvectors psi, and then the total charge density will just be psi squared over the occupied state. So this is how you would solve the single particle problem in quantum mechanics where you don't have any interactions. So we know how to do that, and what we have instead is we have this equation here that does have interactions. It has this exchange correlation potential in it. And we also don't know this. We don't know the functional derivative of the kinetic energy with respect to density. But we know how to solve the non-interacting problem. And what we'll do is we'll just pretend that we have the non-interacting kinetic energy here. And then we have some kind of effective potential here instead of just the simple single particle potential up there. And we'll just solve it in exactly the same way. And so basically, that's what Cohen-Sham theory is you have a quantum system with a set of single particle looking like states, and you solve it by just, I'll mention in a few minutes, diagonalization or some other kind of method. So this is the reason why many people call it, single particle theory, because you are solving a single particle theory. So in principle, your system has to be representable as some kind of single particle result. Okay, so it does mean that there may be certain systems that are not going to work with this Cohen-Sham approach. One may not be able to find an appropriate effective potential that's accurate enough for them, basically. Now, in the local density approximation, what one does is the simplest possible thing. You say that I'm going to assume that this exchange correlation energy is just given by this exchange correlation density at each point that comes from the charge density. So this is just going to be a simple function of the charge density each point, and then we'll just integrate over the density over space. So if we make that approximation and carry through the different definitions I showed before, I showed you the exchange correlation potential should be the functional derivative of the exchange correlation energy with respect to density. And so if you carry this through, you find out that it's just the simple derivative with respect to density of rho times this exchange correlation kernel. So, so that's the LDA. That's the local density approximation. You'll find thousands and thousands of papers being published every year using the local density approximation. And the problem is what is this this little epsilon xc? What is this exchange correlation density, energy density? So it was determined by Dave Sepperly and Bernie Alder in 1980 in this famous paper, which I saw is, I don't know how they figured this, maybe it's number of citations, considered one of the top 10 PRLs of all time. Okay, so this is the paper where they first parameterized the ground state energy of the electron gas using quantum Monte Carlo. So using that, I'll show that in a second. And then using that, you can go ahead and do your calculations. So in fact, this is from that paper, and what they determined was the energy as a function of density, electron density. They use this parameter RS, which you may see in the literature many times in the DFT literature, which is really just related to the charge density. It's how many electrons, what the radius of a sphere is that would have one electron in it in Bohr radii. And they had this curve as a function of density. So as you go up in RS here, you're going to more and more diffuse systems. And just to give you an idea of different elemental metals, what RS is on the order of 3 to 5 or something like that at zero pressure. And so basically what you do then is every point in space has some charge density in a material. And at that point in space, you say the energy density is, just read it off this graph here, and you find many different, even LDA functionals in the literature, and what they are is basically just different, parameterizations, different fits to these numerical results, basically. And people have gone back and done this again and, gotten another decimal place or whatever, but, basically it's the same as if you go back to the original paper. So there's a lot of details to deal with. I'm not going to cover all of them in great exhaustive detail, but I'm going to kind of just mention the chapter headings and say something about them. If you went to a DFT short course, there would probably be a whole hour or two lecture on the total energy and different kind of ways you can get into trouble with it if you were writing a code or something, but I'll just say some brief remarks about it. We know the total energy is a function of the density. We can write this equation in a straightforward way now. I think I've shown it to you several times now already. So you need to evaluate all of these terms accurately. One of the issues with total energy calculations in DFT is that one has a great need for accuracy because total energies are huge numbers. If you looked at the total energy for anything, diamond, whatever, it's some gigantic number, but the bonding energy is maybe in the 8th decimal place or something like this, the 8th significant figure, or the 10th or the 12th significant figure. So we need a method that's very precise numerically. Near the nuclei, we have very large negative potential energy and very large positive kinetic energy, and we have to calculate how those cancel out very much. And really, 15 years really maybe was spent in the field, figuring out how to do this really accurately and then how to get accurate forces and so forth. And it took time to do this where people really knew that they were dealing with the right result. And even now, you'll find calculations done with different codes will not give identical results all the time. And so you can track that down and try to figure out where that's coming from, even when supposedly the same approximations are being made. Usually nowadays that's due to pseudopotentials, which I'll talk about at the end of the talk, rather than any kind of problem with the total energy calculation. But for a long time this was an issue in the total energy calculations as well. So there's actually a lot of subtleties here, and if you use one of the common DFT codes, you'll very often find switches that turn on or off different approximations, for example, to the total energy. So for example, one can write the total energy as a sum of eigenvalues with some correction terms added on. And the reason you can do that is written here on the slide. And I don't know if I really need to go through it, but we can take this single particle looking like Schrodinger equation, multiply it by psi star, sum over all the occupied states, and we find out that there's an expression for the sum of the eigenvalues of the occupied states. It's related to the kinetic energy plus some density functional terms. So you'll find that used in some codes. It turns out, though, when you do a DFT calculation, as I'll be explaining in a minute, it's a cyclic, self-consistent process where one starts with some input density or potential, gets some output density or potential, and then iterates until you have the input and output being equal to each other. So you notice in this expression you have the density here alone. But really, when you're doing the real calculation, there's the input density to the cycle and the output density of the cycle. It turns out that you can rearrange things in such a way that you get a variational expression for the energy in the density using a combination of input and output densities. So there's all kinds of complications that come in order to get accurate numbers during a real calculation. Okay, now I've alluded already many times today already that there are, maybe I should stop and ask, this may be a good point to ask if there's any questions. So this is really the fundamentals, and now I'm going to move on to a little bit kind of the next level. This may be review for everyone in the room, I'm not sure, I don't think so, but for many people I know it's review. Okay, I'm just going to move ahead, but hopefully the basic ideas are clear. Now, one confusion in DFT is that there are many, many different density functionals. And I find that this is a really severe problem among everybody, okay, experimentalists as well as theorists, okay, because the fact that there's different density functionals and different results you can get, many of my experimental friends say, well, theory can't tell you anything because one theorist gives you this answer, another theorist gives you that answer. And then theorists also have this problem that they say, oh, well, that was just an LDA calculation, and we did a better calculation, we did a GGA calculation. But as I showed you earlier on, sometimes the LDA is better than the GGA. So you may have heard the expression ladder of density functionals, which has been kind of popularized by John Perdue, and I don't really think that's a very good way to describe the situation. It makes it sound like you just go up to a more sophisticated, harder to compute functional and you'll get a better result, but it doesn't really work that way, unfortunately. I mean, it'd be nice if it did. But this is kind of the ladder that he's talking about. We start with the LDA, which is just based on the charge density. And I didn't really talk about it, but I'll just say now, the next thing, which is really very closely related and even goes back to the original separately Alder work, is the local spin density approximation, which includes the spin density. So instead of just having the charge density, we now think about the density of up electrons and the density of down electrons. We carry everything through exactly the same as I've shown it up to now, except that now we split the two terms. And now we have an exchange part of the exchange correlation potential and a correlation part of that, which both together will help you describe magnetic systems. So you can do DFT even in the lowest level approximation, local spin density approximation, and for magnetic systems. If you do BCC iron, you'll find that BCC iron is magnetic with a magnetic moment that's not that far off from experiment and so forth. Okay, the next level of approximation is the so-called GGA, or generalized gradient approximation. It includes the gradients of the density and of the spin density, and it's based on exact constraints for the effect of gradients in the density on the energy. And like I showed you before, that improves some properties and not others. Just as a rule of thumb, one of the most obvious things to look at is the total volume of the system. Do you get the volume right at zero pressure? Well, generally, the LDA gives volumes that are too small. It makes things that are too dense. And the GGA tends to make things that are too large. And so some people have now gone, to their more exact method of taking some fraction of LDA and fraction of GGA, but really these are just kind of games. Maybe you can convince yourself that in some class of materials you can get a better approximation from that. But if you read a paper in the literature where somebody did the LDA and they got a volume that was 10% larger than experiment, you can say there's either something wrong with the experiment or something wrong with their calculations. Okay, so generally, I don't know of any really good exceptions. The LDA will give you one sign of the error and GGA the other. And then there are so-called MetaGGAs, which include the kinetic energy density, the Laplacian of the density, and they, of course, are more computationally intensive and maybe have a slightly better result in some cases. So most of these things come in through their approximation of the exchange, and they have an exchange enhancement factor, this f of sub x here, which is related to the gradients and say, the kinetic energy density. Another thing that you'll see a lot of nowadays, which actually I'm not going to talk about at all, but if you're interested, you can look in the literature, is methods that include some fraction of exact exchange. Okay, so they're really just including some part of the Hartree-Fock exchange energy, and so you'll find a lot in the literature, especially in chemistry, using approaches like that. There is an exact form for DFT, and in fact, you can couple this in with QMC, and it's been done. I don't have time to talk about the applications of this really, but there is a literature on this. And what you can do is you can say, imagine that the interaction between the electrons is scaled by some parameter lambda, where lambda is going to go from 0, where you have the non-interacting system, to 1, where you have the fully interacting system. And then we can write the many-body Hamiltonian as being, again, the non-interacting kinetic energy, and then this scaled Coulomb interaction, and some kind of potential that depends on this interaction as well. And then what you can show is that there's this exchange correlation hole. Basically, an electron carves out around it one electron of space that there'll be one electron missing from, and that represents the many-body interactions between the electrons. And we can represent that as a pair correlation function, which you could compute, say, from QMC. And if you integrate that over the coupling constant from 0 to 1 and get this exchange correlation hole, there's an exact expression then. I'm not proving it here, but you can read the literature or textbooks. There's an exact expression for the exchange correlation energy, which depends on the integral. N here is the density. I was using rho before, but here's very often N is used as the density. And then this is exchange correlation hole, which is this non-local object depending on R and R prime. You integrate over this, and you get the exact exchange correlation energy. And so, so in principle, there is an approach. Okay, you see it's non-local, but some of the more sophisticated attempts to go farther with DFT are based on this. And in principle, there's a way to use QMC to develop an exact density functional for a given material. So how well does DFT do? I've already alluded to problems, and but the fact at the beginning I showed examples of how well it worked. Well, so there have been quite a few cases where people have tried to take standard sets of molecules or standard sets of crystals and see how well different functionals work over this set of materials. So, in this paper, for example, by Tao and Purdue, they looked at 5 different density functionals for molecules, solids, and surfaces, and looked at how well different methods used and how well different methods went. They looked at everything from atomization energies, bond lengths, and so forth. But you see unfortunately, I wish they had done this in percent errors, but they wrote down here the absolute errors by over the set by different ones. So you can see that basically even the LDA gave 0.01 angstroms in bond lengths among 96 molecules. I mean, really, that's pretty good. I mean, if you think like, I've been telling you all these problems and everything, but if you look at a large set of molecules, you'll find that, it's really not that bad. And like I told you, using a better density functional doesn't necessarily make the answer any better. When you go to the PBE, which is a gradient generalized gradient correction one, the errors are 0.016, so it's actually gone up a little bit. Okay, it's a little bit worse. Okay, but if you look at something like the atomization energy, you see it's gotten 4 times better when they went to the GGA over the LDA. Okay, so some things get worse, some get better, and they looked at these kinetic energy density functionals as well. Let me just say something about what the GGA. Okay. Well, this is. I guess I have time to talk about this. This is. Since I'm speaking, I get to. I have this time right here. So since I'm talking, I get to highlight, my own work or work of my group over the years. We've dabbled a little bit as well in trying to find better density functionals, and I think that that's really what you need to do. If you want to understand something, you've got to, do it yourself and write a paper on it, and then you can pretend you understand something about it. So we tried to see if we could make a better GGA, and I'll show the rationale for this in a minute, but the reason was that we were working on ferroelectrics, and if we looked at a material like lead titanate, which is a classic ferroelectric, if we applied the LDA, we got quite a good result compared with experiment. If we applied the GGA, just the traditional PBE GGA, we got it, it was disastrous. I mean, I showed you how things were, right within a few percent, but for lead titanate was really a bad actor, and it was just awful. I mean, the C over A was coming out a factor of too big or something, and the volume was off by 20%. I mean, we thought for weeks that there was a bug or something in our code, but there wasn't, And so we wanted to come up with something that worked better, and so we looked at the regular GGA, and I mentioned it has this exchange enhancement factor. And so we wanted to find basically a different exchange enhancement factor than in the PBE. And so what we noticed was this was actually work of Zhigang Wu, who's now a professor at Colorado School of Mines. So he was a postdoc with me at the time. And so what we noticed is that the PBE GGA didn't work very well in diffuse systems. It didn't treat basically tails of atoms very well. And if you have an ionic insulator like a lead titanate, there's a lot of empty space in it, and so there's a lot of tails, and since the atoms are very polarizable, like the lead is very polarizable, the oxygen is very polarizable, and it's a ferroelectric, the things want to move off-center, then if you don't treat those regions of low density right, you get really disastrous problems. So we use the same correlation energy density that's used in the PBE, but for the exchange part, we tried to design a different enhancement factor, which was based on fitting another exact constraint, the exact known constraint for the density functional exchange as a function of this scaled gradient. So what's shown here is this f of x versus this scaled gradient s here, and the PBE is this black curve here, right here, and the MetaGGA, which is the one that has the kinetic energy density, and it is shown here by red, and our one, the WC one, really plots right along the one with the MetaGGA, except it doesn't involve having to compute the kinetic energy density, so it's just as fast as doing a normal GGA. And so we applied that, in our case, just to 18 different solids, some metals and insulators and covalent materials and so forth, and transition metals. And we found that the new GGA was much better for the bond length. These are percent errors, so 0.3% error in the bond length compared with 1 to 2% error in the standard GGA. And the bulk modulus was also much improved over the standard GGA. So we applied this then to lead titanate and barium titanate, for example. And this shows that if you do the regular GGA on lead titanate, you get like 1.2 is the C over A, whereas it should be like 1.07. So basically, you can't do any work in ferroelectrics if you are that far off in how much the system is strained. And the new GGA gave 1.08 compared with 1.07, so it's in very good agreement with the experiment. We've applied it to a lot of different systems since then. And if you look at the, oh, I don't know, is this actually going to do something? Yeah, this is just, okay. I thought this was going to run automatically. There's no reason for this. It's just, okay, forget it. Anyway, it doesn't matter. just if you look at the difference in the different exchange correlation potentials for lead titanate, it's interesting that if you look at the difference in the exchange correlation potential for the LDA and the GGA, for the exchange part of the potential, you see there's quite big differences, even though the whole scale here is still just plus or minus 0.04 electron volts. So, I mean, there's big differences, but there's small numbers compared with what the total potential is. And if we look at the difference between our GGA and the PBE GGA, the differences are quite small, but the differences are mainly out in this bonding region as well as in the core region of the atoms. Okay, so you get a code, and now you're ready to do your DFT calculation. So this is Abinet, and I put it up like this on purpose where you can't read anything. This is the number of choices that you have for exchange correlation potential before you do your calculation. So if you say, well, I'm going to do a DFT, and I'm just going to try each different density functional, and then I'll average them or something, you know. Well, you've got a lot of work to do, okay, because there's a lot of functionals out there. And if you think it's just Abinet that's doing that, this is a quantum chemistry code called NWChem. There's over 100 different density functionals included in there, and this is by no means exhaustive, okay? So you know, there's hundreds and hundreds of different density functionals out there. The one that we did is just one out of these hundreds, you know. And so I'd say that this is a good reason to do QMC, right? Okay, so you do QMC, you know, you do it right, and you get one answer, hopefully, you know. But you know, you do a DFT, or if you read the literature on DFT, you know, you need to look and see what they're actually doing, you know. It's almost better to use LDA in some ways, because if you use LDA, you know, it's a very well-constrained thing. You know what you did. You know, everybody else knows what you did. As soon as you get into one of these modern functionals, you know, maybe your result is some, you know, quirk of that functional. So that, you know, I just throwing this out for you. Different fields will tend to use different functionals. So if you look at chemistry papers, you'll see that they tend to use the Becky-related functionals. If you look at other fields, you'll find people using other functionals. This is a slide. We get to the point in my talk where I started stealing slides from different people, but I'll try to put their name on the slide, and these are all done without permission, but they put them up on the web, so anything that's on the web is free for anybody to use, right? So, this is showing a test set of 40 semiconductor systems, again, looking at the accuracy of different functionals, and so if you do the LDA, you see it's almost, you know, they tend to be, actually, okay, so according to what I told you earlier, you shouldn't find any here that are positive, that you should always get bond lengths that are a little short. So, you know, if I really wanted to do my due diligence, I would go try to find what papers these were and see if they were really true. According to this, there are some examples of systems where the volume comes out too large. I mean, I don't know if that's really true, but that's what's here. If you do the GGA, I told you the volume always comes out too large, but you see here, well, actually they are. Here's 0, okay? So for the GGA, all of the systems that he, you know, looked at came out too large. And he also looked at some that had some fraction of exact exchange in them, and the point that he was making is that, you know, that there's less scatter than there is with the LDA, but still there's really not such a huge difference in the accuracy, you know, on average. You know, maybe for a certain system you'll find a big change. Okay, so I have another 20 minutes, and again I'm going to, maybe there'll be resounding silence, but this is a good point for people to ask about density functionals. Yes, please. You have a question?
It seems to me that if you apply more sophisticated methods, it seems to me that we may get better answers, right? But sometimes you say we don't have better answers. The reason is because of the fundamental limitations of the density functional theory, or we don't apply the sophisticated methods right?
No, I think the methods are being applied correctly. So, I mean, that's always a question, you know, especially somebody comes out with something new, you know, was it properly implemented, you know? So there are tests for that. So, you know, I'm hopefully only showing you result, well, maybe a few of those points in those histograms may not be right, but basically I think everything is applied correctly. So why do they not get better when you apply a better approximation? So I think it comes in that, well, this goes back to something I learned back in my postdoc days, really, from Mike Mail, is that he said, anytime you try to improve on the LDA, it'll get worse, okay? So why is that? Well, the original LDA really has tremendous compensating errors, and I didn't really have time to put slides for that in here. But there's both, but there are places where it's predicting too large a potential, and places where it's producing too small a potential, and they tend to cancel out. And so if you fix one thing, it may not, the cancellation may go away. I mean, this is kind of, you know, it's not physics really. So you really do have a better approximation probably when you go up to these better density functionals. So they're probably right more often of space, you know, and more of space they have a better approximation to what the density functional should be. But they lose some of the cancellation of error. And so, and again, this comes back to the fact, it's really surprising that any of these methods work. It comes back to the fact that the real total energy is an enormous number, whereas the kinetic, the chemically important part of the energy that gives us the lattice constant or the bulk modulus or whatever is only in the 10th significant figure or something. So, you know, people have asked me, you know, like students, very good question. I never really have a good answer. How can you have a theory that, you know, can only predict the total energy accurately to I don't know, 2%, and trust it to 10 decimal places, you know? I mean, that's, you know, so the answer is that, you know, that the errors have to be systematic, so that when you look at quartz or stishovite, or you look at diamond and graphite, you know, most of the error is the same in both diamond and graphite, and that, you know, so that the energy difference between diamond and graphite is coming out correctly. And so most of the part that's coming out wrong has to be something that comes out wrong no matter where the atoms are, you know. So, but that kind of cancellation of error means that, you know, you kind of cross your fingers and hope for the best, you know. So, so I would say, again, we should think of DFT, I mean, it's still very useful and predictive, but, you know, you really shouldn't oversell it either. Nobody should say, you know, we know absolutely what the properties of the system are because we did DFT calculations on it.
Well, I can just make a comment that a lot of these, if you look at this slide where you had all these different guys, all the properties that you measured,
Yes.
you'll notice that since their customers are usually quantum chemists, energies get better and better and better. Like atomization energy is guaranteed to get better, but they don't care about volume. There's no such thing as a volume in quantum chemistry. So they never actually, that's sort of like the third order effect. So a lot of this is sort of evolution of what people want. So they want better, say, binding energies, or better atomization energies, or better van der Waals things, van der Waals binding energies. And so those tend to get better. See, they won't publish the functional unless it gets one of those things better.
Well, I know. I mean, people.
So that
Yeah.
seems to be that the volume, that the geophysics
Yeah.
people have a whole different other list of things
Yeah.
that they need.
Yes, I mean, for example, I mean, your point is well taken. For example, if you're a semiconductor person and your whole thing is you want to predict the right band gap, then you don't care if some other functional gives you a better volume or even a better whatever. I mean, you want it to give the right gap, you know. And most DFTs will not, you know, unless you start adding in some exact exchange. And so that's why you'll see that there's a lot of people, well, certainly that work on semiconductors, they will use some kind of method that includes some exact exchange. And then they'll put in a proportion of exact exchange that gives them the right band gap, you know. So they have designed a method that by design, you know, and this is the danger of it. I mean, we say that we're doing first principles calculations, but if you have a parameter that you're varying in order to get agreement with the experiment, you know, it's based on first principles, but you know, it's not really ab initio, right? So most of the so the simple methods like the LDA and the PVE GGA and even our WC GGA, I mean, they have nothing you can tweak in them. So at least you can say that whatever you get, you get. Some of the other ones in that long list I showed you, they also have a parameter or two that you put in, like the percentage of exact exchange, and you can vary that as well. So as soon as you get into that game, you make, the argument from people that do that is they want to get the right answer, okay, because they want to do something with it. And so they say you can't do anything with it if it's starting off with, a band gap that's off by 50%. So, so they start from a system that gives the right band gap, and then they look at changes in chemistry or structure or something like that. So I think, as you will see from the rest of the course, when you do QMC is not easy. Compared with DFT, DFT is a piece of cake compared with QMC. QMC, it's hard enough to get a ground state energy. If you want to do something like compute a band gap or something like this with QMC, it's quite a bit of work. And it's a lot easier to just try to find a density functional that'll give you the answer that you want. But I think you also have to ask yourself if you're doing physics or not. So, or chemistry or whatever. So that's the state of affairs. Nobody has the perfect density functional. But I still think it's the place to start when you do a study. Okay, so I'm going to talk a little bit about the mechanics, and again, this would be a whole whole day's worth of lectures in a short course on DFT. But you really should know some of these terms because you'll run across them in the literature, and they're even involved in different QMC codes. So you should know this for QMC as well. We solve, generally speaking, we solve DFT using different basis sets. And very often, in a lot of codes, one uses plane waves with pseudopotentials, and so his equation for a plane wave. And you can relate these plane waves to different kinds of grids and wavelets and other sort of gridded methods as well, and transform back and forth to a plane wave representation. In physics, in solid-state physics in particular, you'll find maybe a great majority of studies are done using plane waves. A lot of the early codes just use plane waves because you can easily do everything you need to do. They're very fast and efficient and so forth. In chemistry, things tended to start more from a local perspective, so you find exponentials or so-called Slater-type orbitals and Gaussians as being major basis sets that are used. And the reason that they use the Gaussians a lot is, again, because it's easier to do the integrals over Gaussians than it is to do them over exponentials or over other kinds of bases. Another type of basis set that you'll find very often mentioned, I didn't write them all down, but is the LAPW basis, which is very close to my heart. And what basically you do is you divide space into two regions, a sphere around each atom, and then the interstitial between the spheres. And these spheres are called muffin tin spheres, just historically. And then inside the spheres, one uses atomic-like functions, and they're joined smoothly on the plane waves between the spheres in the interstitial region, and one can get a very accurate representation for all of the electrons using LAPW-like basis. And how do you solve the problem once you have this basis? So I've written this many times in the slides already. You have this expression for the total energy. By the way, I think that many places where I wrote down the energy, I was just writing the energy for the electronic subsystem, but any real code has to include the nuclear repulsions, or the core repulsions also. So that's written over here. And if you look on the web or look in textbooks, very often people forget to write down this term. If you tried to write a code and you forgot about it, you'd get totally wacko results. And this comes down to the some of the finesse of doing these total energy calculations again, because it turns out that this nuclear interaction or core interaction was just between positive objects, and so in principle it blows up. And it's a Coulomb interaction, all of the same sign for an infinite system. So you have to pair that part up with part of the Hartree interaction between the electrons to get rid of the singular piece of that. So there's all kinds of little things you have to worry about. So, but basically you just have this like Awald-like Coulomb term over the cores or the nuclei. So the charge density is a sum of these squared wave functions But a part that I didn't really talk about here, if anyone here doesn't have any background in solid-state physics, it's going to be a very quick introduction here. You also have to consider the K-space sampling because you have to integrate over the Brillouin zone in a periodic system. We represent the basis in terms of not only position but also wave vector. And so we have to solve these single particle equations here that involve this Cohen-Sham potential and these single particle looking orbitals or wave functions, and we're going to do that by solving this secular equation. So basically we have these psi's are going to be represented as these orbitals, and the orbitals will be based on the basis. So there's different ways of solving the problem. If you look at something that has a very compact basis like LAPW or LMTO or Gaussians, you can do it with solving a generalized eigenproblem and doing a full diagonalization using a program like a library like LAPACK or something. You can do an iterative diagonalization which parallelizes better. There are methods that work better on parallel computers, such as the conjugate gradient method, where you basically optimize the total energy in terms of the different coefficients of the wave function. And then an area that's very popular these days is Parnell molecular dynamics, where one actually treats the electronic degrees of freedom on the same basis as the nuclear degrees of freedom. Like I say, I know this is just a whirlwind thing, but you know, each one of these things you can blow up into a whole talk. So when you do a self-consistent calculation, you start out with some kind of initial guess for the density, you compute the Cohen-Sham potential, and then you solve for a new density, you solve the generalized eigenproblem somehow, you compute the total energy, you see if you're converged with what you started with. If you're not, you mix the old and the new, and you come back and cycle through. In each one of these things is a whole literature. So like how you mix the old and the new, it's a whole literature on how you do that, you know, and so forth. So, you know, how you accelerate convergence, you know, so that you make this not have to go through the cycle as many times. And when you're all done, then you can compute the properties. You now have the charge density and so forth. Oh, I mentioned about the Parnell molecular dynamics. One writes an effective Lagrangian that depends not only on the velocities of the nuclei or the cores of the atoms, but also on the effective, call them velocities of the electronic degrees of freedom. One has effective mass for the electronic degrees of freedom as well, this mu here, and then one solves the equations of motion. I mentioned it's not a solid-state physics class, but since you're going to have to worry about K-point sampling if you're doing any of the examples or so forth for crystals, so I mentioned that you have to integrate over the Brillouin zone. This is, for example, the Brillouin zone for I forget what, BCC lattice. And they have different names for different points here. So there's a lot of jargon, okay? So the gamma point is 0, 0, 0, and the L point here is a half, a half, a half, and so forth. So everything has a jargon, and then, you know, it blows up into a whole inscrutable field that if you don't have any background in, could be very hard to walk into. There's different ways of sampling K-points to do this effective integral. Usually you use a finite set of K-points. You need to take some care so that you have the proper symmetry of the system when you do your K-point sampling. If your K-points don't have the symmetry of the system, you may predict improperly that the system should distort, and it really doesn't, and so forth. After you do that, then one has something like a band structure that you can get out. I said there's these different names for the different points in K-space, and you can plot the eigenvalues as a function of where they are in the Brillouin zone. And this, for example, shows you, this is another motivational slide for doing QMC. This shows you the computed band structure for FeO. It predicts FeO to be a metal. It's actually a good insulator. Okay, so this is no matter which density functional you use. There's other things you'll see. Density of states is just how many states there are in each energy range, and people will plot a plot like this, and a partial density of states. You'll color in the different orbitals that are important in different parts of the energy spectrum, and maybe a band gap would appear as a gap here. In this case, there's no gap at the Fermi level. This is FeO again. It's incorrect in DFT, but you can study what DFT gives anyway. And I would say this is one of the big advantages of DFT. By the way, I have like 5 more minutes, okay? So one of the big advantages of DFT is in a very straightforward way you compute these band structures, these complicated spaghetti diagrams, partial density of states, spectral functions, and so forth, and other kinds of optical properties and different things that are, quite inaccessible maybe to conventional QMC methods. So, in QMC, you'll see we're going to try to get a really good, calculation of the total energy, but we're not going to get, a spaghetti diagram out, right? Okay, so there's things that we can learn from DFT. I think that DFT, very much should be used as a complementary partner to QMC studies. So, you can do your QMC study, you can do your DFT study, and you can see where the DFT fails and so forth, but there's still things that you're going to learn from it that you're not going to learn from QMC. Another thing you can do with DFT is you can start taking derivatives of the Schrodinger equation. So you can do what's called density functional perturbation theory. You can do this to very high order and compute directly elastic constants and piezoelectric constants and phonon frequencies and get thermal equations of state and so forth. This shows an example that we did for lead titanate. And we did the frozen phonon method where you basically strain the system and calculate the energy as a function of strain and the change in polarization as a function of strain, and got the different piezoelectric and elastic constants. And then we did it with density functional perturbation theory and got really good agreement with that. This turned out to be an important study because, again, this was work with Zhigang Wu, Michael Wu, but we did this also at high pressure and found that this tremendously interesting phase transition where one got extremely high electromechanical coefficients under pressure. But this is available now in standard codes like ABINET. And I would say that one of the nice things about this field is really the attitude of the people in this field to make everything available, at least the good people do this. So for example, we use this facility for calculating the piezoelectric and elastic constants that was developed in the ABINET code by these authors. And they put it in the code, they put it out for everybody to use before they even wrote a paper with it. I mean, well, they wrote the method down, but they didn't apply it to anything, And they put it out there for people to use, and we, published a PRL based on it, and they just put it out there for everybody, okay? So generally speaking, in the DFT world, you'll find a very open attitude towards sharing methods, sharing codes, and, making things available to people to use. I think it's a good example. You can use these methods for making predictions of properties just in the last few minutes. For example, doing so-called materials by design, like we use this to study, try to find new types of oxynitrides. And so what we were able to do with DFT, which what I think would be pretty hard to do with QMC, is basically take the whole periodic table and say we want to look at perovskites that we replace one of the oxygens with nitrogen, and then we want materials that are stable, that are insulated, or that have a high polarization, that are non-center symmetric, and see if there's anything interesting. And we found this yttrium silicon oxynitride, and then we were able to calculate a whole slew of properties. So we calculated the dielectric properties, the polarization, and all kinds of piezoelectric and electro-optic properties and so forth, all with the ABINET code. And we're basically just hunting for something interesting. And we found that it had huge predicted nonlinear optic coefficients. So we now have a patent on this material based on this prediction, a material that had not yet been made. So you can do stuff like this with publicly available, off-the-shelf codes. You just have to have an idea and then follow through with it. Okay, so I've only got 3 minutes to talk about pseudopotentials, which should be a whole lecture. And I don't know if anybody else is talking about pseudopotentials. So Burkhard, I really only have 3 minutes now for pseudopotentials. So where are we in the schedule? 5 minutes. Okay. Well, I'll do this as quickly as I can, but you need to know something about pseudopotentials, and it just wasn't scheduled anywhere else as far as I know. Maybe if there's time, we can come back. We'll have a lab session making them.
So maybe that's...
On Thursday, we can add more.
Yeah, so maybe we can come back to this later, but I have to say something about it, so I'll just do it quickly. Okay, so there's many reviews, short course notes, lectures, tutorials, etc. on pseudopotentials on the web. Okay, basically the idea is here. Okay, so if we look at the, this is for carbon, if we look at the valence wave functions, you see they have nodes in them, and they get to have more structure near the nucleus and so forth. And when we do either a DFT calculation with plane waves or a QMC calculation, these changes in sign cause problems, and also these, the fact that you have structure near the nucleus. And as you go up in Z to heavier and heavier elements, you get more and more wiggles down here, of course, and it gets harder and harder to represent them. So what you do with the pseudopotential is you find an effective potential that gives you a nodeless wave function that agrees with the correct wave function at some large distance from the nucleus, and then disagrees inside, but matches on above some R cut, above some cutoff out here. The original idea behind pseudopotentials was that all the bonding happens out here, and so who cares if you get this right or not? Now, I don't really think that reasoning is correct, but nevertheless, a tremendous amount of work has been done with pseudopotentials, and it's been very successful. So here's, for example, what a screened pseudopotential looks like for carbon, and you see it doesn't look anything like a 1 over R or a Z over R sort of potential. It's very shallow. Here's that cutoff length. You see it's essentially 0 out here, but there's one bit here that makes life difficult for everyone, and that's the fact that different angular momentum channels, S and P here, have different potentials. This is a so-called non-local pseudopotential. I'll say more about it in the remaining couple minutes, but that causes us all kinds of headaches. And if you try to do this with just a single potential that represents all of the angular momentum states together, it's just not accurate enough. And then we have to unscreen the pseudopotential, taking out basically the valence electron interactions, and this is the final thing that we'll use in the actual calculation. You notice that we ended up with some little wiggles down here, which you generally don't want. So this is the kind of thing that, it's really an art form making good pseudopotentials. And one of the things I want to say is a lot of people use libraries of pseudopotentials that are on the web, and I really want to argue against that because I've found that generally they're not satisfactory. Okay, so you'll find that some library pseudopotential will have like wiggles in it or something that isn't good, and nobody bothered to plot it or whatever. It worked okay for whatever they did. So the basic idea of pseudopotential generation is we start out with the original single particle looking like equation. We write it like this. The eigenvalue is the Hamiltonian acting on the wave function. And then we're going to require that the pseudopotential eigenvalues are almost equal to the real eigenvalues from the all-electron problem. And there's going to be some pseudo eigenvectors and some pseudo-Hamiltonian. So basically, I have a list here. I don't have time to go through the different steps, but there's a set of mechanical steps for finding a pseudopotential. There's different ways of doing it. Here's an example for molybdenum. I already showed the example for carbon, so I'm not going to go through this in any kind of detail. If you apply different methods, though, of making pseudopotentials, you get different pseudopotentials. So it's a non-unique construction. And so literally there are, again, just like there are many, many different density functionals out there, there are many, many different choices of pseudopotentials. And you can make your own, and it's really an infinite set of possible pseudopotential choices to make for any system. And they will give different results. So this is a problem, because we tend to use pseudopotentials in QMC as well. You notice that if you take the Fourier transform of the pseudopotential, they may go to 0 at different rates, meaning that you need different numbers of sizes of basis sets to treat them, say, with plane waves. I mentioned about this issue of non-local pseudopotentials. A local pseudopotential would just be a function of distance from the nucleus, but if it's also dependent on the angular momentum, then it's called a non-local or semi-local pseudopotential. And I don't have time to go through that. Let's see. So I stole this from the web, and this is really nice. So this, I think, it's worth taking an extra minute of my talk to go through. This is from a paper by Hammond, but it's these guys, Junguer and Garcia, who put this talk together on the web. And it's a really nice set of basic principles for making a good pseudopotential. So you want the eigenvalues to agree. So let's say these are the all-electron eigenvalues. These are the pseudopotential eigenvalues. You want them to agree with each other. So that's number one. Okay. Number two, you want the wave functions to agree beyond some cutoff radius, so that if you look at the orbitals outside some distance, you want them to agree. That's kind of a requirement. So all pseudopotential generation methods insist on that. Third, and this is something people tend not to look at, but you should, is that you should check that the logarithmic derivatives of the all-electron and pseudo-wave functions agree at the cutoff. So they don't have to agree, but they should agree. They need to agree in order to get so-called transferability, which means they don't just work for recomputing the atom, but they also work when you apply them in your crystal. This is called norm conserving. This norm conserving constraint is that they have the same amount of charge inside the cutoff radius that the real wave function does. And then there's another requirement of the logarithmic derivative as well, which really is related to the norm conservation. And this is just an example from their thing. So what about pseudopotentials in quantum Monte Carlo? And this is really premature to show this now because you haven't even done any QMC yet.
And we're going to talk about that.
You're going to talk about this in particular?
Yeah.
Okay, so I don't need to say any more. Okay.
On Wednesday.
Okay, good. You'll hear about this on Wednesday. So, so I just want to end with this. We have done some all-electron QMC for solids, and I noticed that Mike Taylor has done some of this as well using a different approach, but this is work of Ken Essler and I and colleagues. And what we did is use an LAPW-like basis, and this was implemented in QMC pack. And what he found to begin with was when he used different pseudopotentials, he got different results for cubic boron nitride. We were trying to make a really accurate equation of state for calibration purposes. And so using different pseudopotentials gave different equations of state. So that's not very good. So what we found, let's see, I'll just go to here. This shows here, this is, see, if you plot them just as pressure versus volume, it seems like everything agrees, okay? So, but the problem is, the importance is in the differences. So if you plot the difference from kind of this general curve here, you get this. And you see that different pseudopotentials represented by these different colored bands here gave very different results. Whereas the experiments were shown here as the point. So you see that, if you want QMC to be so predictive that you can really trust it as well or better than an experiment, then you need to have get over the pseudopotential problem. And so, so we did these all-electron calculations, and were able to really reduce the error to a few GPa to terapascal. Okay, so in the last minute, I just want to say that I recommend using public license open source codes. There are other codes to use. I really am finishing. Okay, so I really recommend Abinet, Quantum Espresso, or also known as PWSCF, QBox. For pseudopotential generation, I recommend the Opium codes, and I would say generally don't trust pseudopotential libraries unless they, you really know that the one that you want to use has been tested. Okay, last slide. So, so in summary then, DFT shows that there's this one-to-one correspondence between the ground state charge density and the external potential. This is an exact theory. It's an exact many-body theory in principle. In practice, it's not exact as we apply it. It's reasonably accurate for many systems, but fails for others. Nevertheless, it's very useful for us to generate trial functions, optimize structures, compute phonons, finite size corrections, and so forth for QMC calculations. We tend to use, we use pseudopotentials to effectively approximately remove core states. And I think a good working knowledge of DFT is really useful for practical QMC calculations. There are many freely available codes, tutorials, and so forth on every aspect of what I've talked about today. Okay, thank you.
Thank you, Ron. Questions?
Yeah, so I have a question about the RS values that you showed for the atoms.
Yes.
And so I understand how you can calculate RS value for a uniform, density, but how do you calculate RS value for a density that is non-uniform?
Well, those were for the average valence density.
Oh, I see. Okay.
Right? So those are the metallic electrons, the ones that are at the Fermi level.
Those questions in the back, and maybe you'll repeat the question for the...
Oh, yeah. Okay, the question was how can we say something about RS for an atom, for a non-uniform system, and when you apply it for something like a a nearly free electron metal, say, for example, then you're asking about why, what is the density of conduction electrons?
And that would be like at zero pressure, right? Or-
At zero pressure,
Yeah. I mean, it's,
yeah.
you have a solid.
Right.
Can I ask two questions?
Yes.
First, you said the LAPW, so you mentioned the deficiency of the DFT, like in ferroelectrics, but can't that be compensated by full electron calculation? So why we have to introduce the QMC? The other question is that you mentioned about in Abunit there are about many different exchange correlations. So even there are many different PBE, different GGA. So is there some general idea to select which PBE, which GGA will? Because it seems one GGA just applies to a specific system. So
Yeah. Okay. So let me answer both of those questions. So the first question was, why do QMC when it works with DFT? I guess is that right?
yeah, basically.
Well, I think that it depends what your question ultimately is. So in the case of I have not done QMC for these ferroelectric problems yet. Okay. Henry Krakauer is doing such calculations. They're very involved because the energy scale is very, very small. So if you want to study like a ferroelectric system, typically they have phase transitions around room temperature or something like this, and the energy wells may be just millivolts. Okay, so to accurately do that is very hard for both the density functional and for QMC. I would like to see QMC calculations done so that we would know what the real answer is. But it is a good question because in ferroelectrics, for example, they're not only a very small energy scale, but they also tend to be quite disordered materials in the sense that all the atoms are not moving in the same direction in the same well. So you have problems of kind of local disorder and so forth as well. So it's really a problem for any method that you use. I think that the answer would be is that if we did QMC or somebody did, and we had that for a system like say lead titanate, then we would have some kind of fundamental thing we could rely on. Let me give you a really good example. You've asked me a question. It's almost like a plant, very close to my heart. Okay, so a big problem in the field right now is ultra high pressure ferroelectricity. So DFT calculations predict that materials like lead titanate, as you go up in pressure, they become less ferroelectric. And it used to be thought they went cubic and became just a cubic perovskite. But then it was discovered that DFT predicts that at really high pressures, like 60 GPa or 100 GPa, it becomes a really good ferroelectric again. Okay, so that's really interesting. And I didn't do that work. That was done by Kornev and Balazs. We repeated their calculations. We got the same results. We tried different density functionals. They all gave the same results. So they said, well, this is a great thing for our experimental colleagues to do. So over the last 5 years, we've done a series of more and more sophisticated high-pressure experiments, and none of them have shown this high pressure for electricity. And so we said, well, maybe it's because the calculations are done at zero temperature and the measurements are being done at room temperature. So we went and did cryogenic measurements at 10 Kelvin and still don't see it. So for example of the type of experiments that have been done is second harmonic generation. One of the things is that if you have a non-centrosymmetric material, then the phonon frequencies, Raman frequencies depend on crystal orientation. So we took crystals and we rotated them at high pressure and low temperature to see whether the phonon frequencies move with orientation. So at low pressures you see it happening and it goes away at high pressure. So all of the experiments that have been done seem to disagree with the DFT calculations. So there's two approaches to take. So the one would be to do QMC. Nobody has done that yet, and that would be saying something's wrong with the density functional. The other is to say it's some kind of quantum paraelectricity. That's the approach that we're taking right now. So we're doing first principles molecular dynamics to try to see if at finite temperatures, even at 10 Kelvin, there's enough motion to wipe out this. So the answer is there are problems, that we just can't trust the result from DFT, and and it's still an unsolved problem. Now the second question was, how do you choose which density functional to use? Okay, so I would say it depends on your problem. I would say that if you have no reason to choose anything, you might as well do LDA. Now, if you know that that the class of system that you're studying from other people's previous studies or whatever, that LDA just isn't going to give you the answer that you want. Like if you want to calculate elastic properties and you know that the LDA elastic constants are better than the GGA ones, I guess you should really do LDA, okay? If you're trying to get a really good value of the volume, of the equation of state, maybe you should do GGA. I mean, that's a really unfortunate answer, but that's the truth, okay? Now, as far as which of the flavors to use, everybody has their favorites, But, so, it kind of depends who you're working with and what their favorite is. We tend to use the WC because we invented it, But that's just, our own idiosyncrasy, So if we don't use it, who will,
There was another question in the back. You're done. Any more questions?
Thank you, Ron.
Okay.
Produced by OCE Atlas Digital Media at the University of Illinois, Urbana-Champaign.